Good morning, everyone, and thank you for being here today. I'm pleased to welcome you to this presentation on calculations for related substances. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, we will explore key concepts and methods involved in the calculation of related substances, which is an important aspect of pharmaceutical analysis and quality control. Over the next few slides, we'll cover the fundamental principles, common techniques, and practical considerations. So let's get started and delve into this essential topic together. Related substances are impurities that are found in a drug substance or a drug product. These impurities are actually structurally related to the active pharmaceutical ingredient, or API. They can appear at various stages, such as during manufacturing, storage, or even as a result of degradation over time. It's important to understand these related substances because they can impact the safety and efficacy of the medication. By identifying and controlling these impurities, we ensure the quality and consistency of the drug. This concept ties into the overall theme of quality assurance in pharmaceutical development and manufacturing. Let's talk about the test for related substances as outlined in monographs. This test essentially covers impurities that can be found during manufacturing, including intermediates and byproducts, as well as degradation products that may form over time. When we perform chromatographic determinations without a reference substance, a common approach is to compare the unknown peak with a peak from a diluted solution of the substance we're examining. This helps us identify and control impurities effectively. Acceptance criteria are carefully established, taking into account several factors. These include the qualification of degradation products, data from accelerated and long-term stability studies, the expected expiry period, and the recommended storage conditions for the drug product. All these parameters ensure that the impurity levels remain within safe and acceptable limits. Now, in cases where we don't have specific data on the quantification and qualification of impurities, there's a fallback. We can refer to the general chapter of the Indian Pharmacopoeia to set workable acceptance criteria. This provides a practical solution when direct data isn't available. Finally, to understand how impurity limits are actually calculated, considering the test and standard or reference concentrations, there's a helpful illustration following this explanation. This helps us grasp the relationship between test results, standards, and permissible impurity levels. So, in summary, this slide emphasizes the importance of thorough impurity testing, the criteria for acceptance, and alternative approaches when data is limited, all of which are crucial for ensuring drug safety and quality. Today, I'll walk you through the chromatographic system setup we're using for analyzing anastrozole and its related substances. First, we have a stainless steel column, which measures 25 centimeters in length and 4.6 millimeters in diameter. It's packed with a phenyl group stationary phase that has particles 5 micrometers in size, providing good separation efficiency. The mobile phase is a carefully prepared mixture. It contains 65 volumes of water, 35 volumes of acetonitrile, and 0.5 volume of orthophosphoric acid. We then adjust the pH to 3 using a 1m sodium hydroxide solution. This pH adjustment is crucial for optimal separation and peak shape. The flow rate of the mobile phase is set at 1 milliliter per minute, which ensures consistent and reproducible results. We set the spectrophotometer to detect at 220 nanometers, as this wavelength is ideal for monitoring the analyte's absorption. When injecting samples, we use a volume of 20 microliters, which balances sensitivity with peak resolution. The solvent mixture we prepare for dissolving the test samples is made by mixing equal parts, 50 volumes of acetonitrile and 50 volumes of water. For sample preparation, we dissolve 50 milligrams of the substance under examination in 100 milliliters of this solvent mixture. To prepare the reference solution, we take 1 milliliter of this test solution and dilute it to 100 milliliters with the same solvent. This helps us compare the test and reference to identify any related substances. Finally, we're analyzing for related substances using liquid chromatography. This method allows us to detect and quantify any impurities or related compounds in the anastrozole sample, ensuring its purity and quality. Now, let's look at how we can calculate the limit of impurities when the area factor isn't directly provided in the monograph. The same formula applies here, just adjust based on the impurity limit given. When performing these calculations, you start by injecting the reference solution. It's important to note that the test isn't considered valid unless the column efficiency is at least 2,000 theoretical plates and the tailing factor doesn't exceed 2. These are quality checks to ensure your chromatography is working properly. Next, you inject both the reference and test solutions. In the chromatogram for the test solution, the area of any secondary peak should be no more than half the area of the main peak seen in the reference chromatogram. That's the 0.5% limit. Additionally, the total area of all secondary peaks combined shouldn't surpass the area of the principal peak in the reference chromatogram, which corresponds to a 1% impurity level. It's also important to ignore any peaks that are less than 0.1 times the area of the reference peak. Those are considered negligible or below the detection limit for practical purposes. For example, in the case of anastrozole, the test concentration is 0.05%, which is 500 ppm, while the reference solution is 0.0005%, or 5 ppm. All these steps help us ensure the impurity levels stay within acceptable limits, maintaining the quality and safety of the pharmaceutical product. This approach ties into the broader theme of quality control in pharmaceutical analysis, ensuring that every batch meets the required standards. Now, let's look at how we evaluate related substances through chromatographic analysis. The key point here is that the total area of all secondary peaks should not exceed the area of the main peak in the reference solution, which contains 1% impurity. This means that when we sum up the areas of all these secondary peaks, it must stay within that limit to ensure the purity of the sample. For the 1% impurity limit, the calculation is straightforward. The combined area of all secondary peaks should be less than or equal to the principal peaks area in the reference chromatogram. Moving on to the 0.5% impurity limit, the rule is a bit more specific. Here, the area of any individual secondary peak must not be more than half the area of the principal peak in the reference chromatogram. In essence, these calculations help us quantify impurities accurately, ensuring quality control. They connect to our overall theme of maintaining product purity and safety through precise analytical techniques. Now, let's discuss the correction factors as per the IP guidelines. If a correction factor is provided in the monograph, you need to multiply it with the area of the impurity peak. Think of it as placing the correction factor in the numerator. Conversely, if a relative response factor, or RRF, is given, then you divide the area by the RRF, so it goes into the denominator. It's important to remember that the correction factor listed in the monograph is actually the reciprocal of the response factor. So, when you obtain the chromatogram for your test solution, you multiply the impurities area by this correction factor to get the adjusted value. Now, moving on to the response factor itself. It tells us how sensitive the detector is to a particular substance compared to a standard. Essentially, it's the ratio of the detector response of the impurity to that of the test substance at the same concentration. This helps us understand how the detector reacts to different substances. A key point here is that we ignore any peaks that have an area less than 0.1 times the area of the peak from the reference solution. This is the 0.1% impurity limit, which is crucial when we're evaluating related substances. Finally, when calculating whether the impurity level exceeds this 0.1% threshold, we base it on these response factors and correction factors to ensure accuracy and consistency in our assessments. On this slide, we're looking at the key aspects of system suitability observations, which include parameters like asymmetry, the number of theoretical plates, resolution, and relative standard deviation, or RSD. It's important to note that these should be assessed according to the monograph, ensuring our method meets the required quality standards. Now, when it comes to sequence arrangement, there's some flexibility. While a typical sequence is outlined here, keep in mind that your in-house procedures might differ, and that's perfectly acceptable as long as the essential steps are followed. Let's go through the sequence quickly. First, we have a blank, which helps us identify any background interference. Next, we prepare the system suitability solution, which often involves combining specified impurities with a working standard or creating an impurity mixture in diluents, all following the monograph. Then, we prepare the reference solution or standard, again according to the monograph, using either impurity standards or the active pharmaceutical ingredient, the API. Moving on, we prepare the sample solutions, sample preparation 1 and 2, either from the drug substance or formulation, in diluent or mobile phase as specified. For the standard preparation, especially when using bracketing, we prepare systems in a way that ensures consistency across the analysis. Now, let's touch on solution preparation specifics. The blank should be prepared exactly as described in the monograph to serve as our control. The system suitability solution is prepared by mixing the specified impurity with the working standard or impurity mixture in diluents, ensuring it closely mimics the actual sample matrix. The reference solution should be prepared following the monograph, typically using impurity standards or the API standard to provide a benchmark for comparison. And finally, the test solution, whether it's the API or the formulation, is prepared in the diluent or mobile phase per the monograph instructions. When working with related substances, it's crucial to use impurity reference standards accurately. This ensures our impurity identification and quantification are precise, maintaining the integrity of the testing process. In summary, all these steps and preparations are vital for ensuring our system is suitable and our results are reliable. They connect directly to the overall theme of method validation and quality control, so attention to detail here is key. Now, when it comes to tablets and capsules, it's important to remember that using the diluted API standard can be very helpful in identifying unknown impurities. Essentially, the total impurities are calculated by adding up all the known impurities plus any unknown ones we might find. This gives us a comprehensive picture of the impurity profile. Also, if a correction factor, or CF, is provided in the monograph or method, be sure to apply it. The CF adjusts for any differences in response factors, ensuring our impurity measurements are accurate. When we're dealing with active pharmaceutical ingredients, or APIs, related substances are a key consideration. These substances include impurities that are structurally similar or related to the API itself. Monitoring these related substances is crucial because they can impact the safety and efficacy of the final product. In summary, understanding how to quantify impurities, whether known or unknown, and applying correction factors when necessary helps us maintain quality control. This step is integral to ensuring our pharmaceuticals meet the required standards and are safe for patient use. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional information you might need. Feel free to contact us at the details provided. And with that, I want to sincerely thank you all for your time and attention today. Your engagement is truly appreciated. Remember, we're committed to supporting you beyond this presentation, so don't hesitate to get in touch. Thanks again, and have a great day.